Hey, you guys, we're going to get started here in just a minute. Let me know that you guys can all hear me. Is the volume okay? Awesome. So we're going to go ahead and get started. A couple problems have already been brought up. So Grace asked for a couple problems from worksheet 4.1. It looks like we also have a problem from worksheet 4.4. I'm going to be going back and forth between some screens because as I wrote up in that message, I forgot to bring home my binder of all my stuff. So I'm kind of going back off of all my original files online. So it's going to take me a minute to get back and forth between everything. So let's go ahead and get started, and let's talk about, let's see. Let's talk about 4.1. So on 4.1, we have problems number 7 and 8. And let's take a look at those. So if we look at that worksheet, let me bring it up for a minute. Number 7, it states that chlorine occurs naturally in only 2 isotopes. We have chlorine 35, which has an atomic mass of 34.9689, and then chlorine 37, which has an atomic mass of 36.9659 AMUs. If the atomic mass of chlorine is 35.53, find the abundance of each isotope. So it's asking you to find the percentage of each isotope. So let's go ahead and take a look at this problem. So again, we are looking at, this is 4.1, number 7. Okay, so let's take a look at this one. So the first thing you need to realize and that you need to understand is this idea of using X. So let me write out some information first. So we're going to have, let me make sure I'm writing this out. So we have chlorine 35, and we were told that it has an atomic mass of 34, excuse me, I said 34 and I wrote 24, 34.9689 AMUs. And then we have atomic number, we have isotope chlorine 37, which has an atomic mass of 36.9659 AMUs. And we're trying to find the percent abundance. So what we want to do is we want to designate one of these as X. So we're going to say that we're going to solve for X. And remember that these percent abundance, since there's only 2 isotopes, these percent abundances need to add to 100%. Or if we want to keep this into just decimal forms, we're going to say that equals 1. So if this ends up being X, this is going to be 1 minus X when we plug it into our problem. So if we think about our problem, what this is going to look like is that the abundance that we have, so we have the total mass, which we know is 35.4, let's see, 53 AMUs, is going to equal, remember, it's the sum of the atomic mass times the percent abundance. So in this case, it's going to be 34.9689 times X. And we're going to add that to, I have to put this down here, 36.9659. And that's going to be 1 minus X. So you're going to do some math. I'm not going to go ahead and go through all the math. I think the most important part is being able to look at this part right here. So you would need to solve for x. Don't forget that in this case, you will need to actually distribute this to isolate x. So what you end up getting is that you get x equals 0.758%, or that's not going to be a percentage. If we multiply that by 100, that means that it's 75.8%. And then, so that would be for chlorine 35. And then for chlorine 37, what we would have is we would have 100% minus 75.8%. And so that other percentage would be 24.2%. So there's number 7. Let me write down a couple things that you guys are asking for. So let me write a couple of their notes down so I don't forget. Station number 8, 3. You want to definitely be able to read mass spectrometers. You want to be able to understand what they mean. So being able to read that chart and being able to calculate your atomic mass based off of that. So do make sure that you go over that. That would be on worksheet 4.1, numbers 8 and 9, or excuse me, 9 and 10 that you want to look at for those problems and that mass spectrometer. You want to be able to also reference what those peaks mean. So notice that the peak height represents the intensity. I think there is a problem on the review sheet that I gave you. So station number, let's see. Oh, maybe there isn't one. There's not one on the review sheet. I thought there was. But definitely want to look at 4.1, number 9 and 10. Okay, let's look very quickly at number 7, or excuse me, at number 8 on the same worksheet. I'm going to set up this problem. I'm not going to solve it all the way, but I'm going to go ahead and set it up so you guys see what I am talking about. So on number 8, we're given some information. We're given some information about magnesium, and it states magnesium occurs naturally in 3 isotopes. We have magnesium 24, which has a mass of 23.985 AMUs and an atomic abundance of 78.99%. Magnesium 25, which has an isotopic mass of 24.9858 AMUs and an abundance of 10%. If the atomic mass of magnesium, the total magnesium is 24.305 AMUs, find the mass number of the last isotope of magnesium. So kind of a mouthful with that one. So let's go ahead and organize our data and some of the information that is given. Again, this is worksheet. This is number 8 on worksheet 4.1. So we want to organize our information. So we have magnesium 24. We are told that it has an isotopic mass of 23.9850. And of course, that's AMUs, which don't forget that stands for atomic mass unit. And this is 78.99%. We have magnesium 25, and this is 24.9858 AMUs. And we are told that this has a percentage of 10. And then we are said that we have this unknown isotope, so we're going to call that isotope X. We don't know the mass. Now we can easily find out the percent abundance because there's only 3 isotopes, so we know that those 3 isotopes have to add to 100%. So if we add these 2 together and we subtract it from 100, we end up getting the percent abundance to be 11.01%. And we are told that the total mass, so the total atomic mass of all of these, is equal to 24.30 AMUs. So if we look at this problem and when we set this problem up, we are trying to figure out what the mass or the isotopic mass of magnesium. Notice that the isotopic mass are closest to this number right here. So here we have magnesium 24. The isotopic mass is very close to 24. Magnesium 25, the isotopic mass is extremely close to 25. So whatever this number ends up being, whatever number it's closest to will be what isotope magnesium is. So if we plug this information in, what we're going to end up getting is we're going to have 24.30 AMUs. This is going to equal the sum of, here we have, let's see, 23.9850, and you're going to multiply that by your decimal. Notice I just changed that into a decimal from the percentage. We're going to add that to 24.9858 times 0.1000. And then, of course, we're going to add that to our x times, I guess I should do a dot for that one so we don't confuse my x and my times, 1101, again, changing that into a percentage. And you want to solve for x. If you solve this out, you end up getting x to be 25.94 AMUs, which means that this is magnesium 24. Daniel, I'll go over elements which are considered metalloids and which ones are not. I'll go over that in just a minute. And Colton, are there any questions about atomic history? You should know some general ideas about that. You should know just some of the main people. So I would definitely review your notes that you took for those videos. There were some videos that we looked over, so I would just quickly review those so that the names and things like that and what they did are kind of familiar. I don't think that there's a lot of questions, but I think there might be one or two. All right, let's go ahead and look at some more problems. So my next problems come from, let's see, worksheet 4.4. Let me bring that up. Give me a minute, you guys. 4.4. Okay, so we have worksheet 4.4. We have numbers. I have numbers 6 and number 7. So let's go ahead and go over those two. Okay. So this is 4.4. I believe there were questions about number 6 and number 7. Let me make sure. Okay, so let's go ahead and look at this. So number 6, we have carbon-14 undergoes beta decay and has a half-life of 5,730 years. And it's used to date fossils, which you guys learned about today in your presentation. So we have some people present on carbon-14. So the first thing that you want to do is write out the decay for carbon-14. You definitely want to be able to do this. So if we know that it's carbon-14, we want to be able to write this into isotope form. So we have 14 on the top. That's our mass number, which again represents the number of protons and the number of neutrons. Down below here is going to be the atomic number, followed by the chemical symbol. It's going to undergo beta decay. So beta decay is that and a -1. And again, the Greek letter beta. Don't forget that these need to add up. So if this is 0 right here, that means that my atomic mass, or excuse me, my mass number hasn't changed. But these two need to add up to be 6. So this is end up going to be 7. And if you look on the periodic table, you see that that represents nitrogen. So here is our decay for carbon-14. It says a sample is only 3.1% radioactive as it should be compared to the carbon from a living organism. How old is that fossil? Now, so we are told that 3.1% is radioactive. So what you want to do is, and this is kind of a weird problem, what you want to do is that you want to assume a certain mass. So I'm going to assume that my starting mass, so I'm going to say m naught, is 100 grams, which means that my mass at time t, or what we're talking about, if my starting mass is 100 grams, my mass at time t would be 3.1 grams. I saw some of you guys do this one a little bit different. I saw some people say that their starting mass was 1 gram and that their mass at time t was 0.031 grams. Either one is fine. I don't like using such small numbers. That's just a preference of mine. So I use 100 and then 3.1. We're also given some other information in the original problem. We are told that the half-life is equal to 5,730 years. And so what we're asked to find is what is the time that has elapsed. So we're going to have to use our equation. Let's see. So if we use our equation, we are told, don't forget that our equation is mt equals m naught 1/2 raised to t over t 1/2. So we're going to start plugging some information in. So we know mt. So let's go ahead and plug that in. I'm going to change my color. So that's 3.1 grams. At m naught, we have 100 grams. This is all raised to 1/2. We don't know our t. This is our unknown. So it's going to be t. And then 1/2, our half-life is 5,730 years. Let's move our 100 over. So we're going to divide by 100 on both sides. Divide by 100. And what we're going to end up getting is 0.031 grams. And that's going to equal 1/2 t 5730. I'm going to leave off the years for now. Now, in order to get this down below, don't forget we talked a little bit about logs, so you need to be able to take the log of this. And let me see something. Try to see if I could scroll down a little bit more. It's not going to let me. All right. Okay, I might have to move on to a new page in just a minute, you guys. Okay, so we're going to take the log of both sides. So we're going to take the log of this. We're going to take the log of this. What this ends up doing to this problem is we're going to have log of 0.031 grams. And actually the grams cancel out. I don't know why I'm keeping grams. And then we're going to have t divided by 5730 times log of 1/2. So again, remember this log takes whatever is in the exponent and brings it out in front. So you're going to do some math. Don't forget to know where your log button is on your calculator. And if you solve and isolate, you should get t, which equals 28,650 years. You might have that rounded a little bit. Maybe you have 28,700,000 years, or excuse me, 28,700 years. Either one is fine. But the big part about this problem is making sure that you use the log correctly. Number 7 is the next one that I have requested. So let's look at the same worksheet. This is 4.4. Number 7, I like number 7 because number 7 you can use a cheat on. So we have a sample of, let's see, that's fermium 253 decays to 6.25%. of its activity in 18 days. What is its half-life? So because it's 6.25%, that's a nice number, because if we think of our half-life, that is one of our half-lives, actually exactly one of our half-lives. So if we have 100%, after my first half-life, I'm going to represent half-life like that, we're going to see that it's going to decay into 50%. After my second half-life, it's going to decay into 25%. After my next half-life, my third half-life, we're going to get 12.5%. And then at my fourth half-life is where we're going to get our 6.25%. I'm running out of room. So what that means is that to get to 6.25% of our original sample left, that means that we had to undergo 4 half-lives. So if we know that 18 days has occurred, we need to take this 18 days. We want to divide it by 4. And we will get our half-life. So we get our half-life to be, we'll say 1/2, is equal to 4.5 days. How do you know when you can use a cheat? You can use a cheat when your percentage is one of these nice round numbers. So notice that the cheat can be used when we have things like 100, 50, 25, 12.5, 6.25. If you're given a percentage like 10%, that's somewhere in between here. So your half-life isn't going to be a nice, straightforward answer. So you want to make sure that you know these kind of made ones. Let's see. How many different decay equations should we know? Just like the basic. You should know the decay equations that we went over in our notes. So we have a couple different ones. You have your alpha, beta, positron emission, and make sure you know how to represent gamma. Will we have to know facts about scientists in station number 6, Marie Curie, and you should know just some general ideas of what they did. So those were in those video notes. So just know some kind of basic ideas like Marie Curie, radioactivity, Albert Einstein, energy equals mass, and things like that. So just some basic ideas. Okay, let's look at station number 8, number 3. So let me go ahead and bring that up. Station number 8. Number 3. Okay, so station number 8, number 3 is another half-life. So let's go ahead and take a look at that. So this is station number 8, and we're looking at number 3. So what it says is that sodium-24 has a half-life of 15 hours. How long will it take for the sample to decay to 25% of its original mass? So in that case, again, you want to think about that idea that 25% is one of those nice round numbers with radioactive decay. So if we have 100% of our sample, after 1 half-life, we're going to have 50%. After 2 half-lives, we're going to have 25%. So there we are at the amount that they're looking at. They're looking for 25% of our original sample. So if we know that 2 half-lives have occurred and we know that each half-life is 15 hours, all we need to do is multiply that by 2, and we get the time passed to be 30 hours. Okay, let's see. I think I'm working through these. 4.4, number 6. Station number 6, let's look at station number 6. Okay, so we have station number 6. And we are going to look at, can you go over number 4, 8, and 10? Number 4, what has higher energy than X-rays? So the highest energy one is going to be gamma. So alpha and beta are lower in energy. So number 4 is going to be gamma. Number 8. For station number 6, Natalie, are you talking about that, or are you talking about the bottom with the people? I'm just kind of wondering which one you're talking about. So in the first half, when you're matching the rays to the ideas, we have number 4 is going to be gamma. Number 8, which has the greatest mass, that's alpha. And because alpha, don't forget that alpha is a helium particle. It has an atomic mass of 4, 2, and then it is, an alpha. Where if we look at beta, beta looks like this. So notice that it actually has pretty much no mass. It's just an electron, which is really low. And then if we look at gamma, of course, gamma has no mass. It's made of nothing, just pure energy. And number 10, if we look at that, does not bend in the magnetic field. We didn't talk too much about that. I think it was in one of the videos that you watched. But if for something to bend in a magnetic field, it has to have a charge. So right here, we have beta has a charge. Beta actually has a negative charge. It's that electron. Alpha has a positive charge. We did talk about that a little bit. So the only one that would not bend in a magnetic field is gamma, because it has no charge. So as it goes through that magnetic field, so if we have something that's positive here and we have something that's negative here, if we have a gamma ray that goes through, it's not going to bend. A beta particle, if it goes through, it's going to bend towards the positive because negatives attract. If we have an alpha particle, it's going to bend towards the negative because, again, that's positive, so it's going to be attracted to that. I will see if I can post the answers to the review exercises, Nicholas, but as I said before, I had left my binder of all my stuff at home, or excuse me, at home. School is my second home, but I left all that stuff at school, and so I don't have it all on me, so I need to see if I can find my digital copy. So I will see if I can do that. Station number 5. Station number 5, you don't need to worry about. That was in the directions. I said don't worry about station number 5. So skip station number 5. There's not too much on there that we actually didn't talk about that. So don't worry about station number 5. You can skip that one. Station number 3. Okay. Station number 3. So if we look at station number 3, we have a couple different isotopes of neon. So we have neon 20, neon 21, and neon 22. We are told their isotopic mass 19.9924, 20.9940, and 21.9914. And then we're told their percentages. So this was 90.84%. This is 0.26%. And this one right here is 8.90%. So knowing that we have both the isotopic mass and the percent abundance, we can then calculate the average atomic mass for neon. So we're going to have the, we'll call this X for now, but this is going to equal the sum of pretty much this times this, plus this times this, plus this times this. So if we were to write this out, it would be 19.9924 times, don't forget to change this into a decimal, 9084 plus 20.9940 times 0.0026 plus 21.9914 times 0.0890. So if we do that and we add those all together, we see that we have 20.18 AMUs. So that would be my average atomic mass for neon based off of that data right there. Let's see. You should know how to use log. So definitely know how to use log in those radioactive decay equations. Can you go over station number 8, number 1? Number 1 is going to be a little bit hard to go over. I will talk about it, but the reason why it's going to be hard to go over is because I don't have the graph. You guys can't see the graph in front of you. So you're given a decay graph off to the right-hand side. So again, I'm looking right now at station number 8, and we're looking at number 1. So it says, what is the half-life of the graphed material? So remember, the half-life is when 50% has decayed. So if you look at that graph and you are told that you start off, it looks like you're starting off with 100 grams, you want to figure out how long does it take for it to go down to 50 grams. So if you read that graph and you go down to 50 and you read over, you see that that line intersects at about 3 hours. So that means that my half-life, based off of that graph, is 3 hours. Then it says, what mass of radioactive isotope will remain after 12 hours? Well, you can see that 12 hours isn't on there, but 12 hours is going to be a whole number isotope. So we want to figure out how many half-lives have occurred. So this is A. B, if we know that there are 12 hours that have passed, we're going to divide that by 3 to figure out how many half-lives have occurred. So it's going to be 4 half-lives. So again, we can think about our decay. We have 50 is going to be 1 half-life. 25 is going to be another half-life. 12.5 is going to be my third half-life. So 6.25% is my other half-life. So after 4 half-lives, there's going to be 6.25%. If we start off with 100 grams and we multiply that by our percentage, we see that 6.25 grams would be left over. And for C, you want to plot a substance with a half-life of 1.5. So all you want to do is, again, starting at 100, note that when 50 grams is left over, it should be crossing your axes at 1.5 hours. If you go down to 25 grams, it should be crossing at 3 hours. So you just want to make sure that that slope is a little bit lower. What 2 elements are liquid at room temperature? That is going to be bromine and mercury. Bromine and mercury are both liquid at room temperature. The first half-life on station number 6. Station number 6, the first half-life. Oh, the first half. Okay. Can you explain electron capture? So when we talk about electron capture, it is using an electron. So if we think of an electron, we talked a little bit about what some of these particles look like. So a proton would have a massive one and would look like that. So that's my proton. A neutron would be 1 and 0. And an electron, if we were to write out its kind of, again, its isotopic mass looks like this. So an electron capture, notice that it's going to be captured. And when you think about capture, you want to think that it's being added. So it's not going to be released, it's going to be added. So if you have electron capture, and an example of this is station number 7, and we're looking at number 4. Here's an example of electron capture, 19K plus, and then you're given a box, 40, and then 18 argon. So what you see, if this is your electron capture, so you look over here, this is going to be 0, 19 going to 18. This has to be a -1 in order for these to add together. So the only thing it could be is electron. This would not be a beta because beta is always released. So this would be electron capture because, as you can see, this is being added to our potassium to produce argon. You do want to know those 7 diatomic elements. Remember, on the periodic table, they look like they form a 7. So we have hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So you definitely want to know those. Station number 7, number 1. Station number 7. Which number 1, the first half or the second half? So let's see. So we have number 1. I think that was Madeline who asked the first half. Okay, cool. So if you are given this problem, so we are given 59, 27, CO, plus 1, 0. So a neutron comes in and hits that cobalt. We produce 56, 25, manganese. And we want to figure out what's being produced right here. So remember, your mass numbers and your atomic numbers end up remaining the same. What I mean by that is that whatever you have on this side needs to be what you have over here. So if we add this together, we see that our top half equals 60 and our bottom part is equal to 27. So whatever we have over here must equal the same thing. So over here we have 56. So what needs to be up here in order to get this to 60? This has to be a 4. Notice that right here we have 25. What do we need to have over here to get that to 27? This has to be a 2. A 4 and a 2 is an alpha particle. Let's see. We need to know, well, we need to know equations for nuclear fission and fusion. You should know what they are. And if you were given an equation, you should be able to write it out just like here, because again, your mass numbers and your atomic numbers end up going over. Oh, thank you, Daniel. Metals and metalloids. So if we look at our metals and metalloids, let me get out my periodic table. So remember that we have that staircase. So which ones are metalloids? So we have our staircase. The first one that you want to be thinking of is silicon. Then we're going to have germanium. Then we're going to have arsenic. Then we're going to have antimony, tellurium, polonium. Astatine and polonium are kind of a little weird. They are debated on whether or not they're metals or non-metals or metalloids. You can kind of keep those as either one. I would not really require you to know those. These ones right here are definitely metalloids. Everything to the right of these would be considered non-metals. Everything to the left of those would be metals. Okay, let's... yes, boron, thank you. Boron is a metalloid. Woo, you guys all came out with that one. Okay, any other questions that you guys want me to go over? What about the lanthanides and actinides? You should know where they are. You should know lanthanides lanthanides and actinides at the bottom. Those are considered metals. And that's really about all you need to know about those. Nicholas, what do you mean about funky decay problems? Can you maybe reference one from either the homework or the station so I can solve that? But you have to be a little bit more specific about which decay ones you're talking about. I hope you guys are comfortable knowing different properties of protons, neutrons, and electrons, being able to write things in isotopic format. Make sure you know your protons, neutrons, electrons, how to calculate those. Also know net charge. We've already done a problem with, let's see, calculating atomic mass from isotopes. Also know about mass spectrometer, and being able to calculate your atomic mass given those. Again, that was on worksheet 4.1, number 9 and number 10. And then let's see, definitely know parts on the periodic table, metals, non-metals, and some of those properties of those. Worksheet 4.46b. Okay, let me look at that. Nicholas, okay, you saw that I did that one? Okay, so I did that one earlier. Nice, Aiden. Very, very accurate definition of what funky is. Yeah, that was one with the 100% thing, so make sure you guys are comfortable with that. Let's see, can you explain net charge? So when we talk about net charge, remember that there are two things within an atom that have a charge. So if we think of parts of an atom, we know that a proton has a positive charge, a +1 charge, and an electron has a -1 charge. So these two things determine the charge. If something has a net charge or is an ion, that means that it has lost or gained electrons. It's not going to lose or gain protons because that's going to change the identity of the element. So you're not going to be changing the number of protons, you're going to be changing the number of electrons. So let's say that if we have an ion and it has a +1 charge, that means that it lost 1 electron. So it has 1 fewer electrons than protons. So let's say that we have carbon, and we know that it's carbon-6, which means that it, or excuse me, we're not going to say carbon-6. Let me erase that. Let's say that we have carbon and it has a +1 charge. We know that carbon has 6 protons, which means that if it has a +1 charge, that means that it's going to have 5 electrons. We can have something with a negative. So let's say that we have something that has a -2 charge. That means that it gained 2 electrons. An example that we can use for that, if we look at oxygen, and let's say that oxygen has a -2 charge, we know that oxygen has 8 protons because it has an atomic number of 8. Therefore, it is going to have 10 electrons. Yeah, Daniel, we'll go ahead and do, let's see, let's look at number 9. We'll do worksheet 4.1. Number 9. I briefly want to sketch out this mass spectrometer. Is there any way I could just condense version of what genres there will be on the test so I can make the best use of my time tonight? Also, Lilo on station 4.1. You need to go through your notes and go through your thing. I'm not going to tell you exactly what's on the test. I don't know. That doesn't seem... So you should know your stations and things that we're going over and study your homework. Okay, so here's our mass spectrometer. We are given some data. Right here is going to be abundance. Right here is going to be mass. So what we would have right here in number 9, we are given a kind of a tall peak right here at 85. And then we are given another peak right here, a little bit shorter at 87. We are told, so this is 100. We were told that according to the data, that this is the abundance is 0.722. And this one, if we were to kind of to look over, this one is 0.278. So what that means is that 72.2% of whatever was put into this mass spectrometer had a mass of 85, and 27.8% of it had a mass of 87. So again, that should look a little bit familiar to what is what we have for atomic masses. So we're given some information, and you'll probably have a data table. So we have 85 right here. We know that it, oh, I am reading too far ahead of this. Your first one right here is not going to be 100, is not going to be that. This is actually going to be 100. So when you actually get your data, this is going to be 85. I should have been looking at the data on the side. This is going to be not the abundance, but the intensity. Sorry, you guys. And it's the largest one is always going to be 100. So 85 is going to be 100. Then we have 87, and the intensity is a lot lower, and that's that's going to be 38.6. Based off of these abundances, we need to be able to calculate our percent abundance. So if what we need to do is that we need to add these two together, so 138.6, and then we're going to divide this by, we're going to take 100, divide it by my 138.6, and then my 38.6, and divide it by this to get our percentages. So this is going to be 0.722, and this is going to be 0.278. This right here is our abundance. And this is the numbers that we're going to be using to calculate our average atomic mass. So we're going to multiply these two, and then we're going to multiply these two, and then we're going to add them together. So if we were to multiply these two, this would end up being 61.3. If we were to multiply these two, this would be 24.2. And when we add these together, that's going to be 85.6 AMUs. And if you look on your periodic table, what that's close to, we see that that is closest to rubidium. So now we could say that according to this mass spectrometer graph, that our substance that was put in was rubidium. All right, let's see some more problems. Let's see. Give me a minute, you guys. Someone wants me to go over station number 4. So I'm going to go ahead and read through those answers. So let's go ahead and identify each substance as being a metal or non-metal, or a semi-metal or metalloid. So shiny and ductile, that is a metal. So ductile, remember, means that it can be drawn into a wire. Poor conductors are nonmetals. On the other hand, very good conductors are metals. Magnesium Mg is an example of a metal, so you want to be able to locate that on the periodic table. If something is brittle, that means that it breaks easily. That's an example of a nonmetal. Arsenic is an example of a semimetal or a metalloid. Argon, if you look at where that is an example of a nonmetal. Also called semiconductors, that is a semi-metal or a metalloid. Silicon, that again is an example of a metalloid. Is a good conductor, that would be an example of a metal. And hydrogen, that is an example of a nonmetal. For an question relating to atomic mass, we'll be having more challenging ones like number 8 on 1.1, or they be more straightforward like number 6. I honestly, I haven't looked at the test since before break, because I wrote the test like 2 months, or excuse me, over 2 weeks ago. I want to say that they're more straightforward like number 6, but you might have something like number 8. I would just know how to do those. Again, I don't have the test right in front of me because I left all my stuff at home, but I would know how to do those. Make sure that you understand how to rearrange those equations, because again, these are simply just rearranging that mean equation that we've looked at, where we have the atomic mass is equal to the sum of the isotopic mass times the percent abundance, and adding those all together. Can you explain the band of stability with ratios of protons and neutrons? Not just protons. It's not just protons and neutrons for the band of stability, because as you increase the number of protons, the need for those protons to want to repel each other gets greater and greater. And so you actually need more neutrons as the mass gets larger, because neutrons kind of act as a buffer. So if you think of those neutrons in between all those protons, we need more neutrons so that that repulsion between those protons don't just rip the nucleus apart. So the band of stability starts to lean more towards neutrons as they get heavier, so that they could withstand all those positive charges in the middle. Again, positive charge things want to repel each other. So when you have a ton of positive charge in the center of a nucleus, they're going to want to fly apart in other directions. Those neutrons help to keep them together. Colton, I wouldn't spend much time on that. Again, I don't want to say off the top of my head for sure that it's not on there, but yeah, I'm not 100% sure. 4.4. Number 8. Okay, this will be the last problem I do, you guys. So let's go ahead and look at station 4.4, number 8. So this will be my last problem. So if we look at station 4.4, number 8, we are told that we have LR257, and it has a half-life of 8 seconds. How long will it take for 75% of the sample to decay? 75% of the sample to decay. Whoops, let me space that out. What you want to think about is that when we talk about something to decay, what that really means is that 75% of the sample decays. That means that we have 25% left. And half-life is really based off of this percentage. So when we think about our half-lives, what we see is that 2 half-lives have occurred in order to have 75%, well, excuse me, this is 1, this is 2. 2 half-lives have occurred in order for 75% of it to decay. So if each half-life is 8 seconds, what that means is that if 2 half-lives have occurred, that means that 16 seconds have passed. The homework packet, which video notes are you turning in? You have to look at the date, and I want to say that they are the video notes that you guys took when I was absent that one day. And if you're not 100% sure, I will go over that. You will have a periodic table on the test. I will give you that, again, just like Aiden says, it's not a green one, it's a red one, but it's the exact same as the green one that you guys have. So you guys will have that periodic table on the test. Don't think that I will cover up the periodic table on the wall that has things labeled. So still make sure you know where all your groups are, because I will be covering that up tomorrow. Okay, you guys, I think that's it for now. I should be at school a little bit early tomorrow, so if you guys have some final answers or some final questions, feel free to stop by. But other than that, good luck studying, and I will see you guys tomorrow. Have a good evening, you guys.